Welcome to this lecture class on cryogenic hydrogen technology. So, in continuation to our earlier lectures on these hydrogen properties, today we will try to cover the sludge hydrogen production and then ortho para conversion and what is ortho and para hydrogen. So, let us start with the sludge hydrogen. In the last class we talked about the hydrogen properties and we have seen that hydrogen is basically low density when it is a very small molecule and it is on the first, it is the first element in the time table, in the periodic table. So, its density in the gaseous form is very low. So, we have to densify it while storing it, and one of the storage means is, as we have learned, that we can compress it, and another form of storage is the liquid hydrogen. Then liquid hydrogen is denser than the compressed hydrogen. Another form of hydrogen is the solid hydrogen. So, that is the third phase of hydrogen, and but we can completely make it solid, but that will not be very convenient thing to transport from one point to the other. So, often what we do is that we make a slurry of solid and liquid. So, these are the some of the keywords. We will talk about the Auger method, then we will talk about the freeze and thaw technique, then we will come to ortho hydrogen and para hydrogen. So, now let us talk about the sludge hydrogen. As I was talking, that it is a slurry of solid and liquid. So, this solid and liquid, we can vary the quantity of solid in the liquid hydrogen, and that will that will determine the density of the resultant solid liquid slurry. So, if we have about 50% of solid in the liquid, we will find the density of the resultant slurry is about 15% higher than the liquid hydrogen at normal boiling point. So, we have the benefit, of course, at the cost of additional refrigeration. But when we are going to use this solid liquid slurry or the sludge hydrogen, we will find that we can have an additional refrigeration of 82.7 kilojoule per kg. So, if we have some amount of liquid hydrogen mixed with solid hydrogen, so that is somewhere in this region, we have talked about it, that this is where solid liquid part would be there, and this solid liquid slurry is basically what we are looking for having higher density and with the additional refrigeration. Now, if we look to the methods of producing this solid liquid slurry, we will go back to our earlier discussion when we have talked about a storage of some amount of liquid hydrogen in a container, and we said that it is a double walled container, and in that context we tried to find out what is the vapor pressure and the boiling point relation. So, if we along with in the phase diagram, if we see that this is where is the critical point and this is the triple point. So, if we have some normal boiling point, the liquid at normal boiling point. So, that is the atmospheric pressure and it is at the corresponding 20.3 Kelvin temperature. So, now if we have this liquid and if we reduce the pressure on top of it, or if we reduce the pressure on top of it, it will follow this line. So, what will happen? The boiling point of the liquid will gradually decrease and it will keep on decreasing till it reaches the triple point temperature. So, that is 13.9 Kelvin. So, at this point all these three phases will coexist. We will have some amount of solid hydrogen, we will have liquid hydrogen as well as we will have vapor. So, that is exactly what we will do in this case, and in the last class we have also tried to solve how this temperature and pressure is varying. So, what we have to do is that we have to somehow reduce the pressure on top of this liquid hydrogen. So, if we are able to take it out this vapor, that will change the temperature of this liquid or the boiling point of this liquid, and we will be able to create some amount of solid. So, let us look how we can do it. So, this is if we plot the temperature the pressure versus time, the time is on this axis and the pressure is on this axis. So, I hope you understand that this pressure would be 7.2 kPa, that is the triple point pressure at which the liquid will exist in the three phases, and the corresponding temperature would be about 13.9 Kelvin. So, initially what we will do is that we will connect it with the vacuum pump to reduce the pressure on top of this liquid. So, what will happen at the triple point temperature, or actually it has to be slightly below the triple point pressure. So, we will reduce the pressure below 7.2 kPa with using the vacuum pump, and at that time what will happen, some amount of solid will be forming on top of this liquid. So, after some time when the solid has formed on top of it, we will find that it is becoming difficult to take out the vapor. So, at that time what will happen, we have to increase the pressure above 7.2 kPa. So, in one cycle we are reducing the pressure, in the other cycle we are increasing the pressure around 7.2 kPa. So, at that time if we consider that this is the solid hydrogen that has formed, that will come inside. So, here this arrow is downward arrow, that means we are slightly pressurizing this system above 7.2 kPa, and that is how this solid hydrogen is coming below, and that is how we will produce, depending on the requirement of the solid hydrogen in the slurry. We have to again start this process, we have to decrease the pressure below 7.2 kPa and again increase it. So, if we look at the diagram, it is taken from this cryogenics journal by Sind in 1970. So, you can see that these are the kind of slurry that has been, or solid hydrogen that has been produced inside the, this is the double walled vessel, and this has come below, and some part is on at the middle, some of the liquid solid hydrogen at the top. So, this is how it is produced for a laboratory scale of slurry hydrogen. But for bulk production of this slurry hydrogen, we may have to take a different route, we call it auger method. So, for producing slurry hydrogen, as we understand that it has to come to nearly 13.9 Kelvin or below 14 Kelvin. So, that this hydrogen will be existing in the solid phase. So, if we have a system or a pipe, say for example, or a tube which is cooled by say liquid helium. So, we are it is a coil wrapped around this tube, and we are sending liquid helium. Liquid helium is colder than hydrogen. In fact, it is the lowest boiling point naturally occurring liquid, and this is liquid helium, its normal boiling point is 4.2 Kelvin. So, if we send this liquid through this coil, this will be cooling this inner surface to, and this is coming out as gaseous helium when it reaches to the top. So, we have some surface, this is the surface which is cooled by liquid helium indirectly, of course. This surface is maintained nearly at 4.2 K. So, now if we pour liquid hydrogen from the top, it will try to come in surface of in contact to this surface, and it will create a solid hydrogen layer on top of this tube. So, if we keep on pouring liquid hydrogen from the top, this will increase the layer of this solid hydrogen. It will keep on increasing, and at some point we will find that this passage is getting blocked. So, what we need to do is that we have to remove this solid hydrogen from time to time. So, for doing that, what we do is we need to have some kind of cutter, we call it auger, and this auger is okay. So, this is cooled by this inner surface is cooled with the liquid helium, and this liquid hydrogen is coming through this top surface, and then we are trying to add one cutter through this. So, this is basically a rotating cutter, and this is the actual picture we have taken from this paper. So, if you have to introduce a kind of rotating device to cut the solid hydrogen from this surface, what we need to do is that we should have the associated bearing attached to the ends of this cutter. So, we have to put some bearing here, we have to add now the liquid from the top. As usual, the liquid helium will be coming from here, and it will become gaseous helium. To cool this inner surface, when this liquid hydrogen is coming contact to this surface, inner surface, this liquid hydrogen is becoming solid hydrogen, and this cutter will cut, and the solid hydrogen will come out from the bottom through this surface, and whatever be the amount of solid hydrogen that you need, you can add it to the liquid hydrogen to generate the solid liquid slurry. So, this is the commercial way of making the sludge hydrogen for densification of the liquid hydrogen. Fine. This is another part of the solid hydrogen or solid liquid hydrogen mixture. Then comes other properties like often we will find that we are talking about normal hydrogen, then we are talking about equilibrium hydrogen. So, what is that? Basically, if you look at, we will find that probably you are familiar with the isotopes of hydrogen. You might have heard that there are two isotopes, one is called deuterium, another one is tritium, or sometime if it is this deuterium is also deuterium water often is called that it is heavy water, and that is used in the nuclear power plant to decelerate the fast moving neutrons. But this is something different, these are spin isomers. If those isotopes are having different mass numbers, here the mass number remains same, but its spins are different. So, now let us look into this hydrogen atom first. So, there is a electron revolving the nucleus, we have one proton inside this nucleus of this hydrogen atom. This hydrogen atoms will have a spin of this nucleus. There is a spin for this electron also. We are not going to talk about the electronic spin at this moment. We are going to talk only about the spin of the nucleus. So, when we combine these two hydrogen atom, this basically they are spin half particles or fermions, and these two spin half particles, when they can combine, or when they will form a hydrogen molecule, they can have a total spin of 1, and this particular combination is having both spin up or both spin down, or basically the degeneracy would be 2 I plus 1, that is 3. So, it will have m equals to 0, plus 1 and minus 1. So, there are 3 3-fold degeneracy with this, and this is called the orthohydrogen. The other possibility is I equals to 0, or the total spin would be 0, and this is basically what is called parahydrogen. So, this is what is known as orthohydrogen, and this is what is known as parahydrogen. So, along with this total spin, they also have the rotational quantum number J. I will not get into the details of this, but what we just want to mention that this parahydrogen and this orthohydrogen, there the difference lies with the J equals to 0 state and J equals to 1 state. These are the the lowest state for the orthohydrogen and the parahydrogen, and this orthohydrogen is having 3-fold degeneracy. So, mostly they will be existing in the J equals to 1 or J equals to 0 will be populated, because this difference in temperature would be more than 516 Kelvin in terms of the temperature. So, here this is the lowest energy state, and if we want to move from lower energy state to higher energy state, what we need is to add heat. But just in opposite way, if it is at higher temperature, if you have to go to this lower lower state, you have to decrease the temperature. So, that is what exactly will happen. You will see that this orthohydrogen at room temperature, if it is there, and if you at low temperature, if we bring it, it will be mostly a parahydrogen. So, this orthohydrogen and parahydrogen, they are basically coexisting at room temperature and with a particular ratio. So, as I have said that this total pins being I equals to 1 and it has 3-fold degeneracy, and this is I equals to 0. So, 2 I plus 1 is basically the single degeneracy. So, total is 4. Out of this 4, 3/4 is orthohydrogen and 1 part is parahydrogen at room temperature. So, that means the orthohydrogen and parahydrogen concentration would be something like this, and it will vary with temperature. So, at this point, so let us look into this orthoparahydrogen concentration. So, we can understand that at nearly 300 Kelvin, we have 75% of orthohydrogen of OH2 and remaining 25% of parahydrogen. So, this is what we call it as normal hydrogen. So, this normal hydrogen this is at gaseous condition, because this temperature is 300 Kelvin, and if it is pressurized or non pressurized, it will be in the gaseous state. And if we now try to liquefy it using any liquefier or at bringing it to somehow to normal boiling point at 20 K, we will have almost all 99.8% of parahydrogen and remaining about 2% is orthohydrogen. So, you can understand this complete gas has been converted into the liquid state, and if it is coming to an equilibrium, then this equilibrium concentration should have been 99.8% para-hydrogen and 2% ortho-hydrogen. So, what it is called that this is how this concentration is going to vary, and if it follows that as the temperature of this gas is lowered, say at about 80 Kelvin, if the it is supposed to have 50% ortho and 50% para. So, if it is able to convert itself from ortho to para by this amount, we call it as equilibrium hydrogen. It may so happen that this gas you have brought it quickly to the liquid state, and then still it may have this 75% ortho and 25% para. It is also possible, but at that time what will happen, this ortho hydrogen will slowly try to convert itself to para hydrogen. As a result, it will release some amount of heat, and that heat will try to evaporate the liquid which is been produced. So, that is not desired. So, we have to look into we should try to convert this normal hydrogen to equilibrium hydrogen, so that as we are liquefying the gas or as we are cooling the gas, we must take care of this conversion, which is basically a slow process. Based on our discussion, what we understand that this ortho and para hydrogen is not only it's important because of this release of heat, but it is also having quite different CV. CV of this ortho and para are quite different, and if we try to plot it, this is 1.5 and this is say 2 and this is 2.5 and this is 2.5 and 3, and in this temperature scale we will be having about 350, around this is 150 K or so. So, this is for the ortho hydrogen. This ortho hydrogen Cb by R ratio will be like this. So, if you look at the para hydrogen, you will find it is something like this, and it is coming around say 150, and it will be something like this. This is for the para hydrogen, and on this side the normal hydrogen would be in between and something like this. So, this CV being different, you need to know exactly whether it is in the para hydrogen you are dealing with, or you are dealing with the ortho hydrogen, or you are dealing with the normal hydrogen. Accordingly, this CV will be different, and that may change the design of your equipment, etc. So, now let us try to conclude. So, these are the references. You can look into the Barron's book or Thomas Flynn, and these are some of the papers we have referred to. Also, you can look at this book by Matter and Method at Low Temperature by Powell. So, conclusion is like that we have talked about the sludge hydrogen production by freeze and thaw technique, as well as auger method, which is a commercially, if you have to produce sludge hydrogen in bulk, you should go for a auger method. Then we have also tried to understand what is ortho hydrogen and what is para hydrogen, and the importance of this ortho and para. So, thank you for your attention.